we have learned in the last class, we have learned how to calculate the bending moment, shear forces for a combined foundation as well. We revised it, and then we have learned how to do the one-way shear and two-way shear check for an isolated foundation. Okay. Today, whatever we are going to do, or today whatever we are going to tackle is going to be related to the analysis of an isolated foundation, but with eccentric loading. Okay. Now I have updated the PowerPoint, and I have sent you the a link rather than the PowerPoint. So every time I do any modification, directly you can find the modified PowerPoint. Okay, so whatever I do at the end of the class, directly you can go and see the PowerPoint. Okay. Whatever problem that I have increased, it's going to be exercise 3.4. Okay, we have solved exercise 3.3 if you remember. Okay. We are going to go for the eccentric footing. Now the eccentric footing normally is not taught to the students of BTech level, but since in a lot of cases in reality we are having eccentric foundation, and you should know how at least you will find the bending moment. Now, if you have seen from a combined foundation, an isolated foundation, the main difference is how would you calculate the bending moment. Now, after that, value of K, Z, AS is going to be repeated. The process is repeated. Okay. Now we are going to learn how to calculate the bending moment for this particular case, and just concentrate with me because this is going to be a combination of a lot of basic things that you have studied from the previous semesters, and it might be uh, the most tricky part of the design that we are having throughout this semester. Okay, except for the lateral loading, this will be the trickiest. Okay. So I have written the problem, which is exercise 3.4. I have written it in the whiteboard. Can you see it in the whiteboard? Can you confirm that you are seeing my screen? Can you confirm that you are seeing my screen? Okay. So the question says we need to design a rectangular pad footing to resist an axial load of 1100 kilonewton from a rectangular column. So normally in my design, or normally if I'm the person who will do the design, I'll just write the inputs here. Okay, so my input says that we have loading. We have a value of P or a value of N, whatever you will call it. Okay, it's going to be 1,000. Can you turn off your mics? 1,100 kilonewton has been given, as stated here. And then we have a rectangular column. So we have the cross section of the column. It will be 500 into 300. It says for me the column longitudinal center line coincide with the longitudinal center line of the foundation. But in the transverse direction, the column center line is 400 mm away from the footing center line, as shown. Now, of course, there was a diagram, but I preferred that you will understand how to draw the diagrams. It's not necessary for me in the exams. I'll bring for you the drawings. Okay. C40 and FY460 are to be used, and the safe bearing capacity can be taken as 250 kilonewton. Now, what we need to understand that we have we have it's a rectangular foundation, so we are going to have something called length, and we're going to have something called width, right? Okay. The line which is going to be parallel, the line that is going to be parallel to the L, if I draw a line here or L, they represent whatever we call it as longitude. The longer direction, okay, we call it longitudinal. The other direction, we call it as transversal. Those who have used software, they will know that in most cases we use transversal and longitudinal, especially for the reinforcement. Now what they say for me, they say it for me, the longitudinal center line, okay, the longitudinal center line of the column coincide with the longitudinal center line of the foundation. So they are in the same line. Okay, but in the transverse direction, you are 400 mm. What does it mean? It means your longitudinal section of the foundation, which is in green now, is going to be the same as the center line of the longitudinal section for the column. Okay, so the green and the gold or brown, they are coinciding, means they are in the same line. Now for the transversal, they said you are 400 mm away. So this is whatever we refer as footing center line. And you are telling me that you are away by 400 mm. So rather than being here, rather than being in this point, you are being 400 mm away. Are we fine? Okay. So once again, we have a column. Okay, we have a column. The column is 500 into 300. Always try to make the longer dimension of the column to go with the longer dimension of the foundation. The shorter dimension of the column to go with the shorter direction of the foundation. Okay. Now, if you say the longitudinal line for the foundation and for the column is in the same line, which is the gold color or the brown color or whatever you are saying. Now, for the transversal, you will see that between the center of the foundation and the center line of the column, we are having 400 mm distance or 400 mm eccentricity. Are we clear? Are we clear? Very good. Now, after understanding the, let us write here C14, then FY 416. Let's say bearing capacity to be 450 kilonewtons. Okay, so these are my inputs. These are the data given. Okay. Now, if the column was a square, then the solution is going to be good. I mean, the solution is going to be easy. We have seen in case of an isolated foundation, whatever we have solved first, it was for a square foundation. Square was easy because you will know that your length and your width are the same. Okay, but in case of a rectangle, they are not the same. So what we need to do in order for me to find in order for me to find the dimension of the foundation, normally what we do, we take a ratio of the dimension of the column. So what do? We say longer dimension. Let me do another. So longer dimension for the column divided by shorter dimension for the column is going to equal longer dimension of the foundation of the footing divided by shorter dimension of the footing. Okay. Now what does it mean? It means to say I can say that 500, which is the dimension of the column, divided by 300 is now going to give me the ratio of L divided by B. Okay, so this is the best way to estimate in case of rectangular foundation. This is the best way to estimate according to the geometry of the column. Okay, so now what we concluded that 500 divided by 300, longer dimension of the column divided by the shorter dimension of the column, will go in the same ratio of the length to the width. And if we do cross multiplication, okay, if we do cross multiplication, then you will see that eventually your B is going to be 300 divided by 500. That is going to give you 0.6 of L. Okay, are we fine? Are we fine that B is equal to 0.6 of L? We have divided 300 into 500. It's a direct multiplication. We shouldn't spend a lot of time on it. Okay. Now, can we get the area of the foundation? Can we get the area of the foundation? We can say that area of foundation is equal to length multiplied by width, where the length is L and the width is 0.6 of L. If you do that, you will get 0.6 for sure. Okay. So it's going to be 0.6 L square. Okay. So the area of foundation for me now is equal to 0.6 of L square. Okay. Now after finding your area, we can go and use our equation. Okay. We can use our equation where our equation says stress is equal to force divided by area, or we have calculated it this way, that my area, if you remember, my area is equal to force divided by stress, or whatever we called it as, say, bearing capacity. Do you remember whatever we had done for the isolated? Area is equal to force divided by, say, bearing capacity. Yes, sure, I didn't understand. Who said the area is not equal to load divided by, say, bearing capacity? Your stress is your, say, bearing capacity. That's the maximum stress can be taken by the soil. Okay. So the force, in this case, the force has been given as 1,100 kilonewton. the force has been given in the question to be 1,100 kilonewton, and we are going to assume 10% as self weight. So 1,100 multiplied by 1.1 as whatever previous classes divided by the safe bearing capacity. That's 250, which will give you so if we have 1,100 multiplied by 1.1 divided by 250, that is going to give you 4.84 meters squared. Okay, 4.84 meters squared. Okay. Now, according to the calculation, we said for 1,000 times, we said we are going to assume the self weight of the foundation is to be 10%. That's why the 0.1. Okay, so we have the area. Now, as long as we have the area, we can go and calculate for L, and we can calculate for V. Okay. Now our equation says area is equal to 0.6 of L squared. Okay. If I go and rearrange the equation, you will see that L is going to be equal to area divided by 0.6 to the under root. Do you agree? Okay. Okay. Now how much is my area? My area is 4.84 divided by 0.6 to the under root. How much is this going to be? So 4.84 divided by 0.6 to the under root. We have it as around 2.84. Okay. So 2.84 meter. Now if my length is 2.84, then my B is how much? We know that area is equal to L into V. So we can say that V is equal to area divided by L. My area is 4.84 divided by 2.84. This is going to give you how much? 1.704. Okay. So what we can say that we are going to use a section of 2.85 into 1.75, for example. Always you will adopt something more than the minimum. These are the minimum, 2.84 and 1.704. We cannot have 1.04 on the side. Okay, so you can do as well. Both of the methods are the same. Okay, both of the methods are the same. Do not confuse yourself. Okay. So add 2.85 into 1.75. Okay. Now after having this would be okay. Okay, this would be okay if we are having only an isolated foundation with the load being in the center. Now this is not the scenario in this case. In this case, the loading is not acting in the center. Now do you remember when we diagrams? Do you remember when we have talked about the pressure diagram? We said if the load is coming at the center, if you remember, we said it's going to be P over A. And we said if the column or the element is not at the center, Then we have PA plus or minus M over Z, or whatever we say it as P over A minus or plus 6M divided by VD squared. Do you remember that we have talked about these things? Did we talk about the pressure? Right. And we say the pressure here is going to, and the pressure here is not going to be uniform. Okay. So we are in case number 2 now, where the loading is not at the center. We need to check now. How to check? We need to get the pressure. Find the pressure. Since my drawing is now acting in this way, we have two values of pressure. One is whatever we call it P maximum, and then the other one is whatever we call it as minimum pressure. Okay. Now we'll calculate both of them. They should be fine. Otherwise, the the foundation will fail. Now, what we try to do, we'll go and calculate Bmax. We said that this Bmax is equal to PA plus 6M divided by 80 squared. And this B minimum is equal to P over A minus 6M 80 squared. Okay. If a person is asking from where this is coming from P over A plus, this is in case of a loss. In case of a center load, you are having it P over A. In case of having a moment, then it is going to be in this shape. This part is going to go down. This part is going to go down. The moment will try to flip your foundation down from this side, and then it's going to go and take it up from the other side. Okay, so here we have it as M over Z. Here we have minus M over Z. Now, if we combine both of them, we combine both of these. If we combine both of these, then we are going to have this shape, where this point is P over A minus M over Z. And this point is P over A plus M over Z. Okay. Where your Z is BD square over 6. So we kept BD square here and we raised the 6 up. Anyhow, according to whatever pressure, maximum pressure equation we have it as P over A force divided by, if you are confusing with P, then you can use F. Okay. So this is pressure. Normally pressure is going to be written this way. Pressure is equal to P over A plus 6M divided by VD square. Okay. Or you can write the BD square in capital, but that's up to you as well. Okay. Now P over A. P, how much is your P value? My P value is going to be, my P value is 1110 multiplied by 1.1, which is for the self weight, divided by the new adopted foundation. That's 2.85 multiplied by 1.75. Okay. So 2.85 multiplied by 1.75 is whatever we have adopted. This is for the first part. second part, which is 6m plus BD square. So we need to multiply 6 by the moment. Now, unfortunately, here we don't have ready moment. Unfortunately, here we don't have ready moment. What do we have? Loading here. The value of the loading is equal to 1100 kilonewton, and the center line is available here. The difference between these two is 400 mm or 0.4 meter. So if I want to calculate the moment is equal to force P multiplied by E, which is the distance. You studied force into distance, so that's going to go 1100 multiplied by 0.4, which will give you how much is the value. How much is the value? 440 kilonewton meter. Okay, so till now we are only applying the basics that you have studied in previous courses. So 440. Now BD square here. BD square, which B and which D? This particular force will be affecting directly your foundation, right? So we have B of the foundation and we have D of the foundation. So this is going to be your B capital. And this is, let's say, this is going to be your D capital. Okay, so we have B and we have D. Okay, so either you call it, that's why I told you, you can call it as BD small or BD capital, and it's better to go BD capital so you will not confuse with the other things. Okay, so our B in this example is a shorter dimension, that's 1.75. That is 1.75, and we need to square the bigger dimension, which is 2.85 square. Okay, 2.85 square. Now, can you calculate for me this value? Give me the values. Can you give me this value?
Excuse me, sir.
Yes.
In the second term, in denominator, you put plus. It's multiplication.
True.
1.7. Yes.
Can you give me the answer now? Can you give me the answer of the first one? The first one. The first portion. How much is the first portion? First portion. This value is how much? 242.6. No, it cannot be 2000. So 242.6. What about this one? What about this value? Neither, just cross check. It cannot be 2006. The second one. Because still we are calculating for the pressure. If you remember, when we are checking the pressure, we check unfactored. This is what we have done in isolated, if you remember. When we start calculation for the bending moment, at that time, we take the ultimate. We said safe bearing capacity is already factored. Okay, so 185. 185.727. Okay. Now, why I'm calculating this? Calculating this as well, which is 428.33. Now you are telling me the load which is generated because of this point load and because of the eccentricity is going to cause you a pressure of 428.33 kilonewton per meter square, and the soil can only take 250, right? The soil can take only 250. Do you agree? In the question it says safe bearing capacity is 250. The pressure caused by the loading is 428. So will the foundation fail? Will the foundation fail? Once again, the soil can take up to 250. You are applying 400. Will it fail? Yes, it will fail. So fails. Now let us check. Let us check for the minimum. Let us check for the minimum. P minimum. Say P minimum. Although that since this is failing already, you need to change the area. But anyhow, just for the sake of completing this, so P over A minus 6M BD square, where BA we just calculated as 242.6. 6M divided by BD square, we just calculated it as 185.727. Is it clear now why I told you to calculate them separately? Because the difference between the first equation of pressure and the second equation of pressure is only minus and plus. Okay, so rather than doing the calculation twice. Okay, so this is going to be 56.873. Okay, now 56.873, is it lesser than 250? Is it lesser than 250? It is lesser than 250 kilonewton per meter square. So this is fine. Now what happens? What happens in this scenario? What happens? I cannot have certain part of the foundation to be safe and certain part of the foundation to be failing. Do you agree? Do you agree that we cannot have certain part to be failing, certain part to be safe? Okay. So how to solve the problem? How to solve the problem of the pressure being high? Okay, what we need to do? We need to go and revise the area. So let's say revised area. So now I'm going to increase my cross section, and let's say I'm going to increase the area of the foundation. And let's say now I'm going to use 3.5 multiplied by 2.5 approximately. Okay, 3.5 divided by 2.5. Okay, now you can take, you are asking me how did you take this value. Once again, you can assume a value, try once again, and it goes up. So for me, I'm assuming I have seen that this is 428, so it's already too large than the 250. It means that the increment in terms of the area should be big as well. Okay, so I have increased my area to 3.5 into 2.5. If the difference is small, then for example, you can go for 3 multiplied by 1.9 or 1.8. But since the difference is huge, you need to increase the area by a larger value. Now let us do the same equations. Now we have P maximum. Now what do we have? We have 1100 multiplied by 1.1 divided by new area now 3.5 multiplied by 2.5. Yeah, if your pressure is not safe, it means that your foundation will sink inside, and you don't want that to happen. I already explained for you the fact that they should be, I mean, the loading should be lesser than the safe bearing capacity of the soil, if you remember. So 6 into 440. So the only difference, okay, the only difference is going to be in the area. So how much is P max? B maximum is, or give me the value, the first value. The first value is how much? The first value. One 38. Okay, so we have 138.285 plus the second value. Second value. You cannot get it to be 300. I mean, total value is 300. Even 300 is fine. I mean, too much. So if we go and multiply 6 into 440 divided by 3.5 divided by 2.5. Yeah, I have forgot the square. Okay, that's why you need to be careful. If I have missed anything, you need to be careful. Okay. So once again, you need to divide by 3.5. So the answer is going to be 86. Okay. So 86.2. Total is going to be how much? Total is going to be how much? 224.489. The square is for 3.5, yes. Not 2.5, for 3.5. You are squaring the D, the bigger dimension. Okay, so this is in kilonewton per meter square. It is B into D square. B is a shorter direction, D is a bigger direction, so 3.5 is a square. Now, is it lesser? Is it lesser than the 250? Is 224 lesser than 250? Okay, so this is lesser than 250, so it means that it's safe now. Let us go for B minimum. Okay, B minimum. So we have 138.285 plus, sorry, not plus, minus 86.2, and the answer is going to be how much? 52.085. Is this lesser than 250? So is it clear now why I have increased the area of the foundation? Is it clear why I have increased the value of the size of the foundation? Is it clear? In the first scenario, it was failing. Okay, in the first scenario, it was failing. Okay, and then in the next scenario, we increase the area, so it will take into account the eccentricity value. Okay. Now, after we have done this particular thing, after we have done this particular thing, we need to calculate now. We need to calculate, let us say, revised area, and we'll go and calculate the moment. You need to be careful whenever we are going to calculate for the moment. Okay. Now, for calculation of moment, do we use ultimate pressure or surface pressure to calculate the moment? Are we going to use ultimate limit state or serviceability limit state? We are going to use ULS, right? We said, if you remember, for calculation of area, calculation of deflection, we use service limit state because these are actual. For bending, for shear, we use ultimate, right? So now, since we are going to calculate for bending, Okay, we need to use ultimate pressure. Okay. Now, can you help me finding the ultimate pressure? Can we say PULT, maximum ultimate pressure for the maximum, because we have maximum and minimum. Okay. Now, for ultimate pressure, when we calculate for bending, do we consider the self weight? Do we consider the self weight when we calculate for the moment? We said no. If you remember, I have given you the justification. We said when you cast the foundation, already it will be bent. It will take a lot of time for you to develop the loading from the column, which will cause you the real bending. Okay, so that's why we are not including the self weight. So now we have force divided by the area, which is 3.5 into 2.5. Now we need to multiply the force. We need to multiply the force by a factor of safety, right? We need to multiply the force by a factor of safety. Now, did it say for you that this is dead or live? Did it say for you that this is live or dead? Did the question mention anywhere that these are dead or live? We return back to the question. Did they say anywhere that this 1100 kilonewton is dead or live? So there is nowhere they have mentioned that this is dead or live. So we are not sure whether it's dead or live. Now in this scenario, what we do normally, the factor of safety for the live load is how much? The factor of safety for the live load is 1.4. The factor of safety for the dead load is 1.6. Okay. So what we do, we take the average. We take the average. We take the average factor of safety, since this is not known to be live load or dead load. After that, we have finished from P over A. We are going to go for the moment. Now for the moment, we have used 6 multiplied by 440, and then we had 2.5 multiplied by 3.5 squared, right? And once again, since this is a moment, since it's a load, which will cause you to have a pressure, it needs to be factored. Did they mention for you that this is life or death once again? Did they mention that this is life or death? No, the load was not mentioned from the beginning. So for me, once again, I'll be using the average. Okay, the average between 1.4 and 1.6 is 1.5. Okay. Now, can you give me the final answer here? Can you give me this final answer? The first portion and then the second portion. The first portion and then the second portion. First portion is 188, 188.57. Okay, and the second one, second portion, second portion is 129.306, 129.306 or 31, let's say. Okay, so the final answer is 370. Okay. Once again, the actual pressure, the actual pressure which is going to be happening from the loading is 224. But when we design, we are not going to design for 224. We design for something higher. That's why we are having a value which is 317. So nobody should go and compare the maximum or the ultimate pressure here and compare it with the safe bearing capacity. Okay, you cannot compare two things which are already factored. The factor, we said the safe bearing capacity has been already factored from the beginning, and you are now taking another factor, so it's double factors. So 317. Can we have the the ultimate, which is for the minimum? For the minimum, it's going to be 188.57 minus 129.31, right? Do you agree? Which one? Which one of them? Which part? Okay. Now, for those who have studied, studied geotechnical engineering, too, they can correct me, but you used to take a factor of safety to calculate the safe bearing capacity, right? If you remember, I have already given you, I told you, QS, safe bearing capacity, is equal to QL, ultimate, divided by factor of safety. Those who are having geo, do you agree with me? Those who have finished or they are taking geo now, do you agree that safe bearing capacity equals to ultimate bearing capacity divided by factor of safety? It means that for you to reach to safe bearing capacity, that you have already taken a factor of safety. Okay, you have already taken a factor of safety. Now there is no point of taking another factor of safety. Are we okay? Are we fine? Yeah, I have repeated it for 400 times now. I said we have two limit states. One limit state is for calculation of deflection, because for the deflection we consider the actual load. I cannot consider something which is not happening. The same thing for the area. The area will go based on the actual loading. Now, for the moment, I think I have given you the example of the chair. If you remember, we said if my weight is, for example, 100, I'll not go and design the chair for 100. I'll be designing the chair, for example, for 150. Okay, so I have taken extra load as a factor of safety. That's the ultimate case. Okay, that's the ultimate limit state. Now, in case of service limit state, which is the actual condition, if my weight is 100, then the deflection is going to be 400. It's not going to be 150. So for the deflection and area calculation, we use a service limit state. And for calculation of bending and shear, we use ultimate. Okay. Now we have got our ultimate. Okay, we have got our ultimate pressure for the maximum and the minimum. Now, what we are trying to say. So I just came here and draw my footing, and we said we have a pressure here. We said we have a pressure here. Now this pressure value, you said for me that this is 59.265, and you told me that this pressure is 317.80, and this is how the pressure diagram will go. Now my column, My column is available here. The total length of the foundation is 3.5. Half of the foundation is 1.75. And you told me from the center of the column till the center of the foundation is 0.4. Okay, now we want this dimension. Okay, we want this dimension because actually we require to calculate the moment at this face, and we require the moment at this face. If you remember, we said moments to be calculated at the face of the column. The moments are to be calculated at the face of the column. Okay, so can you tell me how much is this distance? Now, if you see the column actually in this direction was 300. It means from here to here we have it as 150. So if this is 150, then this is going to go as, okay, this is going to go how much? As 250.
Excuse me, sir.
Yes,
Please check. Is it 300 or 500 should be there?
okay, that's true. So this is 300 then, and this is 500. So if this is 500, then this is 250. Okay, half of the column is 250. So if this is 250, then this is going to give you 150. So now the total length from this point to here, if this is 0.15, then this is going to give you 1.9. Okay, once again, good that you are following with me, because I don't normally solve in papers and then write directly. I'm writing directly, solving in front of you. Okay, so if there is anything
Yes,
directly,
sir.
yes,
How did you get the 0.15?
the distance from the center of the column to the center of foundation is 0.4. Half of the column is 250, so the remaining, of course, is 150. Agree? So if this is 1.9, can you tell me how much is this? How much is this? So we have this one to be 1.9. How much is this? The distance from here to here. How much is it? The distance. The distance from here, the distance from here till the end of the foundation is going to be equal to 3.5 minus 1.9. That is going to give you around 2.2 point. How much? Okay, it's going to give you around 1.6. Okay, so we have it as 1.6, and after 1.6, there is 500 here. So this is going to go for 1.1, right? So 1.1 plus 1.9 is going to give you 3 meter, and then the remaining is the column, which is half meter. Do you agree? Can you check the calculation? Everything is fine? Which part is small? Which part which is again? 1.5 or 1.9? Okay, 1.9 plus 0.5 is going to give you 2.4. 2.4 minus 3.5 will give you 1.1. Are we fine? Okay. Okay. Now, after whatever we have done, after whatever we have done, so I'll just open a new whiteboard because there's no place here. So what we agreed, we have a foundation here, and then we have a column. The distance from here to here, it is 1.9. The distance from here to here is 0.5. The distance from here to here is 1.1. Okay, this is not to the scale, but anyhow, 1.9, 0.5, and then 1.1. And we have drawn a pressure diagram of this shape. Here your loading is how much? How much is the minimum? 59.26, I think. 59.26. Okay. And then the other side. How much is 300? 317. 317.88. Now what we want you to go and calculate the bending moment here in the first phase, and then the bending moment in the second phase. Can you tell me how would you do that? How would you calculate the moments? Let's say that this is P1, or not P1, let's call it as, okay, let's say P1, this is P2. You cannot use W square root because this is not a uniform. The loading here is not uniform. It's a trapezoidal, right? You can see that the loading is trapezoidal. So how will you calculate it? Okay. Okay, then you have the length and then you have the B. Your B, is it UDL? Your P, is it uniform value or is it changing? Changing. So it means that you cannot use WL square over 2. WL square over 2 is for a cantilever and a UDL. This is not a UDL. Okay. Now how we are going to do it? Okay. How would you use the triangle? Let us say I'm going to divide it. I'm going to divide it in this way. Okay, I'm going to divide it into this way, where one is no, where one is going to be, okay, if you mean the height of the triangle, then just say no. Now the total The total is 317. This one from here to here, this will go as 317.88 minus 59.26. Can you give me this value? How much is this value? 258.62. Okay. Now can you tell me the pressure in this point and the pressure in this point? P1. Do you agree for me that P1 is equal to this value plus this? Do you agree that it is the black color plus, let's say, the red color? Do you agree that B1 is equal to the black color plus the red color? So the black color is 59.26. The red color, you can use the triangles. Okay, you can use the triangles. You can use the triangles. You already know that this distance is 1.9 meters. Okay, you should know that this distance is 1.9 meters. Okay, so what I'm going to do, 1.9 divided by 3.5 multiplied by the difference, which is 258. Once again, for the height for 3.5 meter, the height for 3.5 meter is 258. How much is the height for 1.9? It's a cross multiplication. X divided by 1.9 is equal to 258 divided by 3.5. So your X equals to 258.62 multiplied by 1.9 divided by 3.5. This is what we have done here. Do you agree? Agree? Okay. So the value is going to be the P1 value. P1 value is going to equal 199.65 kilonewton per meter square. Now going for B2. Now do you agree B2 is equal to the black color plus the green color? Where the black color is 59.26, it didn't change because it's a rectangle. And then the green color is going to be 3.5, which is the total, divided by the distance from here. Okay. The distance from here, how much is the distance? 2.4. So 2.4, 1.9 plus 0.5. 1.9 minus 1.9 plus 0.5, that's 2.4, divided by 3.5 multiplied by 258.62. The final answer is going to be how much? You can take it from the other side, both are fine. Okay. But if you are taking it from the other side, you need to subtract it from 258. once again. Okay. So 236 point, let's say 0.6. Okay. Once again, if you want to take 1.1, you are going to take which meeting? You are inside the meeting. You mean you cannot see the screen? Okay. So now we are having 236.6 kilonewton per meter square. Okay. Now, if we try to further analyze it, we have a column here. Okay. What do we have? We have a rectangle here, and then after a rectangle, we have a triangle, which is this portion. Okay. Now for the other portion, same thing. We are going to have a rectangle, and then after a rectangle, what do we have? We have something like this. Which is representing let me just draw it. Okay. Okay. So I try to separate them. Anyhow, we know that this point, okay, we know that this is 59.26. Okay. And this is 59.26. Okay. Now this has been calculated as 258.62. Can you tell me how much is here? How much is B2? B1 and B2. B1 was calculated as 199.26. B2 has been calculated as 236.6. So I'm going to take this first part first, and try to analyze it. So we have 59.26. 59.26. The distance is 1.9. The distance is 1.9. Now what I'm trying to do, I want to calculate the moment here. We want to calculate the moment here. Okay. So this is going to be as WL square over 2. Or you shift the UDL to a point load and then multiply by the distance. So if we shift the UDL into a point load, it is going to be 59.26 multiplied by 1.9. Now this is my force, which is a point load. If I want to calculate the moment, I'll multiply my force by the distance, which is 1.9 divided by 2. Or we can use our moment equation, which is W, that's 59.26 multiplied by L square, which is 1.9 multiplied by 1.9 divided by 2. So both of them are something same. Okay. Can you give me this value? Can you give me this value? Can you give me the value here? 106. 106.94. Now, how many sheep we have in the left side? How many sheep we have in the left side? How many sheep we have in the left side? We have two sheeps. This is the first one. So let's say this is sheep number. This is sheep number 1. Sheep number 2. Sheep number 2. What is the shape of number 2? The shape of number 2 is a rectangle. So when I go and get the force, and I'm going to get the force will be acting on the one third of the right angle. Do you agree? 1/3 of the length of from the right angle for a triangle. Do you agree? Agree? Now, how to find the force? First, how to find the force? The force equals to half of the base. The base is 1.9 multiplied by the height. What's the height of the triangle? The height of the triangle is going to be how much? The height of the triangle. Can you check for me how much is the height of the triangle? The total is 199. The total is 199. How much is this portion? How much is that portion? Can we say it is going to be 199.26 minus 59.26? Can I say like that? Okay, can I say it's like that? Oh. Okay. Now can you give me the answer of the force? Can you give me the answer of the force? Can you give me the answer of the force? $133. Whatever, 133.33 or 0.37, whatever is right. Now this is in kilonewton. Okay, this is in kilonewton per meter. Okay. If you are assuming the width is 2 meter, 2.5, you need to multiply it by 2.5. If you are considering it to be 1 meter, then keep it as 1 meter. It does not matter. 199.65, 199.26. So when you will go and solve, go and correctly do it. Okay. You are using a calculator. I'm just following whatever you are telling me. So I cannot keep on erasing each and every time. Okay. So as long as the answers 133 and 133.37, those are fine. Now to find the moment. Moment is equal to force multiplied by distance. The force now is 133 or 133.37, what you said. Multiplied by the distance. Now what's the distance between the force to the section of moment? The distance is going to be L over 3. That is going to be 1.9 divided by 3. Can you give me this value? Remember that this is still in kilonewton per meter. Okay. It is how much? 84.40. 84.47. 46.47. Okay. So this is in kilonewton. This is in kilonewton. Now if we add the first value, to the second value, we can get the moment in this point that is equal 106.94 plus 84 into 0.47, which will give you a value of approximately 191.43 kilonewton. Now, if you are considering 1 meter, if you are designing for 1 meter, it's going to be kilonewton meter. If you are designing for the full width, then it's going to be 191.43 multiplied by 2.5, which is the width in this scenario. And how much is your width? And how much is the total value? Once again, if you are designing for a width of 1 meter, you can take it as 191.43. If you are designing for the full width, you want to calculate the moment for the full width, you just multiply it by 2.5. Both of them are okay. How much is the value here? And for me, always I recommend if there is more than one loop or there is inconsistency of the pressure, I would rather multiply by the width rather than multiplying by 1. Okay, we multiply by 1 when it comes to an isolated with a regular loading. Okay, so 478, but both of the solutions are fine. 57 kilonewton. Now one person will say for me, how come that both solutions are fine? One is 191, the other one is 478. I will tell him, in the first scenario, your steel is going to be calculated for only 1 meter, and then the second scenario, your steel is calculated for a width of 2.5. Okay. Now this is the first part. Now going for the second part, which is here. Hopefully we'll finish before the time. Okay. So once again, I just try to do it quickly. Okay. So this is now being a rectangle. Okay. So we can go and calculate shape number 1. Okay. Now for shape, 2 shapes, you don't need 3 shapes. Okay, 2 shapes. So this is 1.1. This is 236.6. So you can calculate it by having 236.6 multiplied by 1.1 to convert it to a point load. And then the distance from here to here, once again, is half of the length. Can you give me this answer? Or you can use W square over 2 since it's a rectangle. Now shape number 2. Shape number 2. So this is 143.14. Shape number 2. Shape number 2. Now if you can see this one is 236. This is 258. So how much is this portion? Can you tell me? For the triangle, once again, this one is 236. This is 258. What is this portion? That portion is going to be, or to calculate the force, we need to have half multiplied by the distance, that's 1.1, multiplied by 258.62 minus 236.6. Can you give me the answer of the force? The answer of the force, 12.1. 12.661, 12.11, whatever is the value. Okay. So 12.11. Now if we take the rectangle, the distance is 1.1. Your force is available here, and you want to calculate the moment in where? I want to calculate the moment at the face of the column. So it's at the far. Okay. So I want to calculate the moment here. How much is this distance? This distance is going to be 2/3 of L. So my moment is going to go as 12.11 multiplied by 2 into L. My L for shape number 2 is 1.1 divided by 3. Can you give me this value? Quickly, please, because we are finishing. So we have it as 8.8. Okay. So 8.88 total moment is going to be 8.88 for the triangle, which is shape number 2, and then plus 143.143 for the shape number 1. The total moment is going to be how much? Okay. So it's going to go 152. Once again, just later on, cross check the values, and then once again we're multiplying it by 2.5. Cross check the values, okay, because you are the one handling the calculator. So can you check how much is this value? $380.057 kilonewton. Now we have two moments. This is moment number 2. This is moment number 1. So the moment in this scenario, not the pressure, the moment is equal to 478. And then the moment in this location, not the pressure, the moment. Pressure diagram is different from the bending moment diagram. Is equal to how much? 380. Now which one is higher? Which one is higher of the two? Which one is the higher value of the two? Which one is the higher value of the two? The higher value is M. Okay. So you are going to design for M, taking into account after finding M, you will go and calculate your K. After calculating K, you calculate your Z, and then calculate AS. Now this is for one direction only. For the other direction, the pressure is going to be uniform. Okay. For the other direction, the pressure is going to be uniform, and the reason we don't have eccentricity in the other direction. Eccentricity is only available in the longer direction. If you remember, we have eccentricity only in one direction. We don't have it in the other direction. So the other direction is going to be a regular isolated case. Okay. So we have taken a full class just to illustrate how would you calculate the bending moment in case of an isolated foundation which is eccentric. Now we have a lot of eccentric cases here in reality, like neighbor column. Like whenever you are having lateral loading, normally there will be eccentricity or moment, and you need to design for it. Anyhow, doing that, we have finished the class. And once again, just revise the values, whatever I have illustrated here. Just revise them because you are the one handling the calculator. When we consider strip or strap. Strip is for a wall or strap. Those who are having in class, we have finished. If you have any question, you can ask. Strap.